We have all wondered what made Archimedes jump out of his bathtub and run through the streets of Ithaca shouting, Eureka, Eureka. What was Archimedes' brilliant idea? And what is Archimedes' principle? Consider this object submerged in water. So this blue stuff is water, and this object might be a stone which is in the process of sinking, or it might be a piece of wood that has been released underwater and it might be in the process of accelerating upwards. It doesn't matter. We are going to first look at the forces acting on it. There are two forces acting on it. One is its weight, and weight is the force of gravity exerted by the earth, and let's call that W, and that force is going to be the same mg whether the object is underwater or not. It doesn't matter. So we have a formula for the weight that is equal to mass of the object times g. The second force is the force exerted by the surrounding liquid. The surrounding water exerts a force on it opposite to gravity. This force B is called buoyancy. Now Archimedes' first brilliant idea is that this buoyancy force which is exerted by the surrounding liquid will not depend on the material of which this object is made. After all, the liquid is acting on it in all directions on the surface, so it might depend on the shape of the object, it might depend on the volume of the object, but it will not depend on the material of which the object is made. If I just consider the surface of the object, I can replace the material by, let us say, wood. The buoyancy force will be the same. Or I replace it with whatever makes a stone, silicon dioxide or whatever. The buoyancy force remains the same. Or I might just replace it with just plain air. It doesn't matter. The buoyancy force is going to remain the same. So Archimedes' second brilliant idea is let's replace it with the same water that surrounds it. So now it just becomes just a piece of water inside a lake. Any chunk of water is in equilibrium. So this is just a chunk of water inside a lake and it is in equilibrium. That means the buoyancy force acting on it should be the same as its weight. So here we have weight of that much liquid. Archimedes called it weight of the liquid displaced. Why did he call it weight of the liquid displaced? Because before the object came in, this volume was filled with the liquid, and when we place the object there, it simply pushed the liquid out. So that's the amount of liquid that got displaced, which is the liquid that occupied this same volume. And the buoyancy force, which is equal to the weight of the liquid displaced, is going to be the same buoyancy force on whatever material I place within the surface. So, whether it's a stone or a piece of wood or anything, the buoyancy force is given by a simple formula, which is the weight of the liquid, the same amount of liquid displaced. So what will be the formula? Start with the volume of the object. Now that volume is filled with the liquid, so density of water gives me the mass of the liquid displaced, multiplied by g gives me the weight of the liquid displaced. And this is called Archimedes' principle. I would have called it Archimedes' formula, but no one consults me. So this is called Archimedes' principle. Now let me show you how to use this in solving two problems. Problem number one, a stone of mass 2 kilograms, let's draw that, and relative density 2 is submerged in water. What is its acceleration? So first let me explain what relative density is. Relative density of an object is density of the object divided by density of water. Let the density of water be rho water. By the way, that is 1000 kilograms per cubic meter, but we may not need it in this problem. Let us see. And therefore, the density of the object in this problem, since the relative density is 2, is twice the density of water. Now let's look at the forces acting on this object. There is the weight and there is the buoyancy. So the weight is given by the volume of the stone, the total volume, multiplied by its density, which is twice the density of water, multiplied by g. Volume multiplied by its density gives me the mass. Mass multiplied by g gives me its weight. The buoyancy force, on the other hand, is given by the same volume, which is the volume of the liquid displaced, multiplied by density of water gives me the mass of the liquid displaced, multiplied by g gives me the weight of the liquid displaced. So the net force is downwards. It's equal to, the net force is equal to V, density of water, times G. W minus B. This is the net downward force. So the acceleration is going to be this downward force divided by its mass. So let's do that. V, density of water, times G, the net force, divided by the mass. So the mass of the object is the total volume of the object multiplied by its density, which is twice the density of water. So you see, density of water cancels, volume cancels, and I get the answer g by 2. G by, so the stone is sinking with an acceleration of 5 meters per second squared. Let's go on to problem number 2. Problem number 2. A block of wood of relative density 0.6 floats on water. What fraction of its volume is submerged? So let's first draw the diagram. Let's say that is the block of wood. As always, we draw the forces acting on it. There is the weight and there is the buoyancy. It's floating, which means the buoyancy is equal to the weight because it's in equilibrium. It's neither accelerating up nor down. So this is the equation that we need to write. So the buoyancy is equal to the weight of the water displaced. How much water is displaced? This volume that is submerged. So let us start by saying, let the fraction of the volume submerged, which we are trying to find out, let it be F. Let the total volume of the solid be V. Then F times V is the volume that is underwater. That is the volume of the liquid that has been displaced. Multiplied by the density of water gives me the mass of the liquid displaced. Multiplied by G gives me the weight of the liquid displaced, and that's the buoyancy. And the buoyancy is equal to the weight. And what is the weight? Again, start with the total volume of the object multiplied by the density of the wooden object. That gives me the mass of the object times G. So G cancels and the volume V cancels, giving us the fraction submerged is density of the object divided by density of water. But this is nothing but the relative density of the object, which is 0.6. Which means a fraction 0.6 of the object is underwater and a fraction 0.4 is outside. In other words, 60% of the object is submerged and 40% is outside. You can see from this calculation that if the relative density had been 0.7 and this object was floating in water, then 70% would be submerged, 30% would be outside. If this was a piece of ice whose relative density is, let's say, 0.95, then we'd conclude that the piece of ice would be floating with 95% submerged and 5% outside. That's it for this video. Thank you.